Here's how we quantify that. We quantify that with a quantity that's called the moment of inertia. Moment of inertia is abbreviated capital I, and it's going to be different depending on how the mass is distributed in a rotating object. So we're going to have a different I for every different type of a device. We'll look at some I's for some simple devices here. As they start to get complicated and asymmetrical and misshapen, then you require some more advanced mathematics or some experiment to figure out what moment of inertia is. So the relationship then, the analog, is this. F equals ma is analogous to torque equals not m, but moment of inertia times alpha, where moment of inertia depends, remember, on two things. Where is the mass and how much mass is present. Those are the two factors that go into moment of inertia. Let's take a look at some common situations. This is actually an imaginary one. A massless rod doesn't exist, but there are lots of situations that can be modeled by this and come out fairly closely. People who have the ability to calculate these things using calculus have given us these different I values. The I for such a situation is just equal to m times r squared. You take the mass and multiply by the square of the radius, and that's I. And then you can put that in that analog equation. Here's another common situation, a thin ring that's rolling or that's spinning. So it's going around like this, a thin ring. Well, here's what I is for that. It's identical, mr squared. So this is just like a lot of little point masses on massless rods. So same I for that kind of an object. Another one is a rolling or spinning disk. So you have this disk and it's going in this direction, spinning around and around. For an object like this, I turns out to be 1/2 mr squared. That's I for a rolling disk or a spinning disk. A sphere, like a golf ball. Say you have an axis here and it's spinning around that axis inside its own center of gravity. Well, for a sphere, I turns out to be 2/5 mr squared. A thick ring, something like the old-fashioned coins that used to have a hole in the middle, or there are some gears that have a large hole in the center. If you have an inside radius that's R1 and an outside radius that's R2, this is I for a thick ring. It's 1/2 m times R1 squared plus R2 squared. A flipping disk. Here's a guy flipping a coin, so it's rotating around its long axis. It's not for a rolling disk. This is a disk that's going around this way, spinning around like a flipping coin. Well, for a flipping disk, I is equal to 1/4 times mr squared. Here's another situation that could exist. Here's a rod. This rod has a length that we're going to call L from one end to the other, and it's spinning around its end. So here's the pivot point, and it's going around in a circle like this. Well, I for something like this is m times L squared divided by 3. Another situation you could have is you could have a rod that has a length L, but it's not spinning around its end, it's spinning around its center, right? It's spinning around its middle. In that case, I is going to be equal to m times L squared over 12. These are just a few of the common ones, and you would find quite a few other ones if you looked in a more extensive list of these things. And then there are a lot of unusual and asymmetrical kind of shaped objects that are going to have really bizarre eyes that could be found through calculus or through experiment. Well, here's an example problem. A solid disk and a thin ring both have the same mass and diameter. So here's a solid disk, has a diameter d, we're going to call it, and its mass is m. So like a piece of wood or steel or something that's cut into a cylinder. Now imagine a different thing, a very thin ring with most of the mass concentrated in the outside, but it has the same diameter as the disk, and it has the same mass as the disk. Now here's the question. If I roll both of these things down a ramp, starting from the same time, which one is going to get to the bottom first? In other words, which one is going to accelerate faster? Stop the video and make a prediction, and I'll come back with the actual film of this happening, and we'll see if you're right, and then I'll explain what happened.
Well, I'm here with Mr. Booth, and we've got two different blocks here. They're both cylinders. Mr. Booth has a solid one there made of wood, and then he has one that's hollow, and it's made of, looks like brass. So it'll weigh more per unit mass, but it's hollow. So they both have the same mass exactly, and if you look at them closely, you can see they both have the same diameter too. All right, Mr. Booth, you're going to put them on top of the ramp. We finally found a good use for chemistry books. You can make lamps out of them, it turns out. Okay, ready, get set, go.
Well, one way of explaining this is to just say, well, the mass is more concentrated on the outside, the R is bigger for the average piece of mass, and that means that you're going to have, it's going to be harder to get it to move in the ring than it would be in the block. But you can also take a more rigorous approach to this too, and let's think about this cylinder going down a ramp. The forces on it are going to be the same forces we always see with ramps. There's force normal, there's a force parallel, and then there is this reactive force. And there's a force of friction, but for an object that's rolling, that force of friction is not applied at the same point as an object that's sliding. It's down here at the base where the force normal is applied. And the reason that it rolls, the reason that it spins at all, is because of force of parallel having a torque, applying a torque over a lever arm that's equal to the radius here. So thinking about our equation here that relates torque to angular acceleration, it's torque equals I times alpha, and that means that alpha for both of the blocks is going to be equal to the torque that's on them divided by whatever I is for that particular object. Now, in both cases, torque is equal to the parallel force times the radius of the disk, and they have the same weight and the same diameter, so that means that these are equal for both of the two disks, and that's going to be divided by I. So the only thing that's really different between the wooden disk and the thin ring made of brass is what's I. And for the thin ring, we know that I is equal to mr squared, but for the disk, for the wooden disk, I is equal to 1/2 mr squared. So the difference between the two in terms of angular acceleration, both of them are force parallel times R divided by I, but I for the ring is mr squared, and alpha for the disk is going to be mr squared divided by 2. And this works out to Fp times R times 2 divided by mr squared. If you simplify these things a little bit, it's really easy to see what the relationship is. R drops out from top and bottom, and alpha for the ring ends up being Fp over mr, and alpha for the wooden disk ends up being 2 times Fp over mr. It's supposed to be an F there. So, in fact, the angular acceleration for the disk is going to be double the angular acceleration for the ring. So, no big surprise that the disk made it down the ramp first. We're going to take a look at another situation where the effect of where the mass is has a big influence on acceleration. We're going to watch a figure skater attempt to break a record for how fast she can spin. She's got a little device attached to a belt that she's wearing around her waist that can measure her angular velocity, her omega. And she wants to make that go faster and faster. Watch what she does with the position of her mass as she goes through this attempt. Here she's going to begin to spin. Look at where her legs and arms are. They're spread way out. As she wants to go faster and faster, they get closer and closer together. Well, what was going on there was she was attempting to make her I smaller, her moment of inertia smaller, so there would be less resistance to her change in motion, and she would therefore speed up. So as she went faster, she made her R smaller. She essentially moved her radius in by pulling in her limbs. Let's watch it again. Slow spin, weight spread out, pulls the mass in, she spins faster and faster. Let's try another example problem. Here we have a meter stick, which we can imagine is a thin rod. It's suspended from the ceiling. There's a string at both ends, so it's held up on both sides. We are given its weight, and the question is, what's the angular acceleration of the meter stick when the string on the right side breaks? So one of the strings breaks, and the thing will begin to spin. Let's start out by modeling this meter stick with a free body diagram. So I'm going to try and draw a straight line there. There's my meter stick, suspended on both ends by a string. In the middle, the center of gravity, so half a meter from the end, would be our weight, which is a 2 Newton force acting downward. And we're supposed to find out what's alpha. That's the question here. Well, here's what we know. The torque that's set up here is going to be equal to I times alpha. So that means alpha is torque divided by I. Let's quantify what torque is. Torque is just force times lever arm, if you recall from previous chapter here. That means that if I have my force of 2.0 newtons, and if it's the right string is breaking, so this would be my natural pivot point down here on the left end, that means my lever arm is a half a meter. So the torque would be 1 Newton meter. Okay, what's I then? The other thing we needed was I. Well, for a thin rod that rotates around its end, ml squared over 3 is what I is. Well, we got to find m. The force of weight is m times g, so that means the mass is going to be the force of weight divided by g. That in this case would be 2 newtons divided by g, 9.80 meters per square second, and that ends up being 0.204 kilograms. So taking that as mass and the length as a meter, we can calculate what I is. I is 0.204 kilograms times 1 meter squared divided by 3. If you calculate I, you get 0.068 kilogram meters squared. So let's take I that we've just calculated. Let's take the torque that we've just calculated, and let's plug them in here and find out what acceleration is here. Well, torque was supposed to go on top, and that's 1.0 Newton meters. But a Newton meter is a kilogram meter per second squared times another meter. So kilogram meter squared per second squared. In the denominator we have I, which is 0.068 kilogram meters squared. So the kilogram meters squared part just cancels out, and we get nice acceleration, angular acceleration units of per seconds. When you do the arithmetic, you find out that it's 14.7 per square second. 14.7 radians per second per second. Well, this is a problem related to the last problem. It's the same meter stick, suspended level, the string breaks, and then we're supposed to calculate how much time will it take for the meter stick to swing vertical. Well, swinging vertical means that it's going to do a 90-degree angle here. So theta would be actually pi over 2 if you're talking about radians. Well, let's solve this problem. Well, once again, our meter stick is going to go through an angle of pi over 2 as it swings. Here's what we know about during the acceleration, what's happening to theta. Theta is equal to initial omega times time plus alpha over 2 times time squared. Well, just as the string breaks, that's 0. And we know what theta is. Theta is going to be our pi over 2. So what we're trying to find in this equation is delta t. Well, let's solve for it. If I multiply both sides by 2 and divide both sides by alpha, I get that 2 theta over alpha is equal to delta t squared. So that means that the square root of that would be delta t. So now I'll just plug in information. I know that pi over 2 is the theta that I'm going to experience. And from the last problem, angular acceleration is 14.7 per square seconds. So when I do this arithmetic, I end up with 0.46 seconds. It's going to take just under half a second.